In this video, we are going to evaluate the value of a Riemann integral using the ideas of upper and lower sum and showing that those upper and lower sums are in fact equal. Notice here we're taking an integral from 0 to 2 of x cubed dx. So with 0 and 2, those are our values of a and b. So a is 0 and b is 2. Also notice that our function f of x is going to be x cubed. And we'll just observe that this function is increasing on the interval that we're interested in. So on the interval from on the interval from 0 to 2, this is an increasing function. All right, so we have this increasing function. Let's, for each natural number, consider the partition P sub n, which is equal to 0, 2 over n, 4 over n, 6 over n, all the way up through 2 times n minus 1 over n, and then 2 times n over n, which is 2. And so we're going to consider that partition. For this partition, the change in x of I is going to be equal to 2 over n for all of those subintervals. Right, so we just keep going up by 2 over n, 2 over n, 2 over n. So that is our delta x sub I. We observed that this was an increasing function earlier, and so since this is an increasing function, m sub I, which is, remember, this is our maximum, like the supremum of all the function values on some interval. So such that x is in a particular subinterval. So if we're talking about the ith subinterval, we're looking at 2 times I minus 1 over n, comma 2I over n. So that's the ith subinterval. Because this is an increasing function, the supremum, the upper bound, that's going to occur at the right-hand endpoint. And so our function value at that right-hand endpoint is 2I over n cubed, which is 8I cubed over n cubed. Similarly, our infimum, our lower values of those function values, are going to occur at the left endpoints. So again, we get 8. Here we have I minus 1 cubed over n cubed. So those are the values of m sub I, capital M sub I, and little m sub I. And so then if we use those to try to identify our upper and lower sums, the upper sum of f associated with this partition associated with p sub n is a sum I equals 1 through n. So we're going to add up over all of those I subintervals. We're going to take the function value, so that 8I cubed over n cubed, times the width, 2 over n. So we're adding up all of those. And using some rules of summations, so sum of I cubed. If we use some of our rules of summations, we end up getting that this is ultimately equal to 16 over n to the fourth times 1 cubed plus 2 cubed plus n cubed. Right, so we were able to factor out all of the stuff other than the I cubed, all the stuff that was not changing. And then there is a formula that says the sum of that I cubed from I equals 1 to n, that is n squared times n plus 1 squared all over 4. And so we get 4n plus 1 squared over n squared as our upper sum. For a lower sum, we have a sum I equals 1 to n. So we add up over all of those subintervals. We take the function value, which is 8 times I minus 1 cubed over n cubed times 2 over n. So all of the lower function values times the width. And so again, we get 16 over n to the fourth. Now we're going to first start with 0 cubed, and then 1 cubed, and then 2 cubed. And we don't go all the way to n cubed, instead we stop at n minus 1 cubed. So that same formula from before, it actually still works. So we have 16 over n to the fourth. So instead of this stopping at n, we're going to have n minus 1 where we stop. So n minus 1 squared times n minus 1 plus 1. So that will just be n squared over 4, which is 4 times n minus 1 squared over n squared. Beautiful. So those are the upper and lower sums associated with these partitions. We can then take those upper and lower sums, and if we took a limit as n goes to infinity, so the limit as n goes to infinity of this upper sum, which is right up here, for n plus 1 squared over n squared, we will find that that is ultimately equal to 4. And we will also find that the limit as n goes to infinity for this lower sum that is also going to be equal to 4 when you take a limit, this limit. And so you could use L'Hopital's rule to evaluate those. You would get some indeterminate form stuff. So you could evaluate those. So because of this, we know that the upper sum, or the upper integral, is going to be less than or equal to 4. We know that the lower integral should be greater than or equal to 4. And because we must have the lower integral being less than or equal to the upper integral, then both of them are equal to 4. So this just gives us an upper bound on the upper integral. It gives us a lower bound on our lower integral. So we get equality to 4, and thus the integral from 0 to 2 of x cubed dx, that is ultimately equal to 4. Beautiful. All right, so that's how you can use our definition to roll through this, these ideas of upper and lower integrals. All right, we will talk to you guys later.